So now we're going to talk about what we call the design criteria for a separator when we talk about liquid gas separator. And here we will specifically talk about the separators that look at or separate or can separate liquid from the gas stream if the liquid droplet is around 150 micrometer and larger diameter droplet, because smaller than this one you will need a demister to collect that one, and you will see in the next few slides that even with the demister there will be certain value or certain size of droplet that you cannot that cannot be collected even with the demister itself. And normally when we design the flow rate, for example, for a gas liquid separator, we design it based on the severest condition, what we call the Q max or the Q adjusted, or the Q that consider the margin, for example, or that consider a certain margin for safety for operation as well. And based on that we can simplify that. Let me just change the color. We can simplify that Q will be equal to Qg as per this formula multiplied rho g divided by rho L minus rho g, which is the difference between the liquid density and the gas density, all to the power half, where Q is the volumetric flow rate or the volumetric load factor that I'm going to look at or I'm going to design based on. Qg is what we call the volumetric of the gas flow rate, and there is a new term called Q max, and this Q max will be the maximum value of Q, or the maximum value or the maximum value for the Q that I will base my design on, where Q max is based on the value of Q. So Q max is in fact is very similar to Q, but for this Q that you will calculate it from this formula, okay, so this Q that we're going to calculate it from this formula, you will have to add a margin, and this margin will look for like what we call the over design margin, the safety margin, or the surging margin, and this margin take into consideration certain safety, over design, and surging factors, and based on that the Q max will be greater than Q, and the Q max will be the value that you will do your design on, and the Q max or the margin that you will be adding to the Q value will be different based on the operation that you are looking at or the application that you are looking at. For example, if you are dealing with oil processing, the margin will be between 15 to 25%. If you are dealing with oil production, the margin will be around 50%. So this is the difference between Q max and the Q. Q can be calculated from this formula, and this Q is what we call the volumetric load factor. But this volumetric load factor, if you have an ideal scenario where you do not take into consideration any other factors or any other parameters such as safety, over design, or other operational issues. So in order to account for this, you find what we call the Q max, where you include all these margins into the value of Q, and the value as a result of Q max will be greater than the value of Q, and this Q max is the value that you will base your design on. The second thing when we talk about design criteria for a separator is what we call the efficiency or the separation factor, or the separation or efficiency of what we call the separation factor of any separator, which give you an indication of how much liquid can be removed from this gas stream, for example. So the separation will give you an idea or will give you an indication about, for example, if you have here a flow of gas and this gas has, for example, water in it, or liquid, let's say water in it in general, and then you're gonna get like what we call this like a vertical separator, let me put it this way, okay, then you're gonna get like relatively a pure gas stream that have a slight amount of liquid droplets. So the efficiency will give you an idea about how much of the liquid you are removing or separating from the original gas stream, or how much of the water or liquid droplet will be removed from the feed gas stream once you do, or once the feed gas stream is fed to a separator. So this is what we call the efficiency or the separator, which is defined as the fraction or the percentage of the liquid entering the vessel that will be separated, which means that it's a ratio between how much you are getting here in terms of liquid to how much originally is here in terms of liquid, which is going to be very little quantity, and this gives you an idea about the amount or the separation factor. Normally the separation also will take into consideration the fact that sometimes you will need a demister, and the demister will be dealing with droplet size of relatively less than 150 micrometer, but normally if you go below 20 micrometer the demister will not be able to collect any of these liquid particle, and as a result these liquid particle will pass through the demister and will go with the flow and will go with the gas flowing. And normally the demister or the efficiency of the demister will be 99% as long as the droplet of the liquid is between 150 and 20 approximately. Below 20 the efficiency will drop drastically and there will be really no major or no major separation. This table gives you an idea about the efficiency expected if you are dealing with different, for example, type of separator, if you are dealing with knockout drum, if you are dealing with the demister or cyclone, for example. And this is like what we call the baton or the type of flow, which is the bubbly, the stratified, and the annular, where the stratified, for example, is the flow when you're dealing with fluid that has different densities, and you can see the flow of material flowing on top of each other, where you see layers on top of each other. The bubbly flow when you have, like for example, gas bubble entrapped in a liquid, and these are several type of flow pattern. Now let's move to the third requirement or the third design criteria for separator, which is what we call the liquid handling requirement, which is always crucial when we look at the capacity of the separator to handle liquid, which means that we have to make sure that the separator can handle the liquid, and at the same time the liquid will not mix again with the gas that's flowing up from the separator or leaving the separator. Otherwise what will happen, you will separate the gas from the liquid, and again the liquid will move up into the separator and mix with gas, and again you have to separate this liquid from the gas stream as well. And in order to do that, normally we will have always to look at what we call the velocity of, or the liquid velocity should always satisfy the following statement, which is this statement. So in order to be in the safe side, this statement always has to stand, which means that Qg divided by pi over 4 dV square should be always less than 2.18 multiplied 10 to the power minus 2 divided by gamma L, which is where gamma L is the liquid kinetic viscosity multiplied, this whole term is multiplied by the difference in density divided by the difference by the density of the liquid, where dV is the internal diameter of the separator. And also here we need to understand that we need to apply the control as well, because we need to control the level of the liquid inside the separators. And I think you know this from the control or from the plant design, which is the level controller, or what we call the level alarm, the low level alarm and the high level alarm. Normally if you are applying automatic control, you will need to have a difference between the two, the low level alarm and the high level alarm, 4 to 5 minutes. And if you are doing manual control, the difference between the low level alarm and the high level alarm should be around 20 minutes, which means that you will give time for the operator to run to that valve or to run to that separator and start to do the action on that valve specifically. Again, how the design approach, or how we're gonna do the design, or what are the main criteria for the design, is the vapor capacity one, where the vapor capacity will help you to determine how much is the cross-sectional area or the diameter of the separator that you are looking for to do the separation, or due to the gravitational force, in order to remove the liquid from the gas. So first of all, the vapor capacity will help you to determine how much is the cross-sectional area or the diameter of the separator needed to provide sufficient or efficient gravitational force to remove the liquid droplets from the gas. The second one is the liquid capacity, where the liquid capacity will be determining the volume required to provide adequate resistance time, which means that we will look at how much is the total volume of, or the height of the separator that's required to do the separation between the gas and the liquid, and allow the degas of the liquid stream, and also allow the separation in case you have two immiscible liquids phases, which we are when we talk about three-phase separators. And the last one is the operability, or what we call the issue that's related to the operation of the separator, including how to deal with solid material, if you have solid material also included, also where you have liquid, gas and solid, how you're going to deal with this, including unsteady state, flow, and some other issues or technical issues that might face any operation. And at the end of the day, you have to come up with a design approach that includes all these three parameters. And this design approach has to always keep in mind that you need to look at the cost, because it doesn't make any sense. It doesn't make sense to have or to design a separator to operate at certain condition that will cost you, for example, too much money for just to do basic separation. So the cost issue has to be always included in the design approach. It has to be always in the equation. Now let's look at separator without mist. Separator without mist are not very frequent or not commonly used for the industry, but there are still some application where you can find the separator without mist. And the most common one, separator without mist, is what we call the flare knockout drum, which is one common separator without mist. And when we talk about separator without mist, you have to keep in mind that the mist is used normally to separate particle or droplet in the range less than 150 micrometer. This means that we are dealing, if we don't need a mist, this means that we are dealing with water droplet that has much higher than the common one, which is the 150 micrometer. This means that if I'm using separator without mist or the mister, this means that I have liquid droplet in the range between 300 to 2000 micrometer, and therefore I can find the length of that separator by assuming that the time needed for the gas flow from the inlet of that separator to the outlet of that separator will be equal to the time required for the droplet of liquid to drop or to fall from the top of the vessel to the bottom of the vessel. And therefore the length therefore the length of the separator to its diameter as a function of the settling velocity, assuming no liquid retention, can be calculated as per this equation. L equal to this equation, where dV is the diameter of the vessel, QA is the actual gas flow, and L is what we call seam to seam length vessel. And you have to remember that when we talk about seam to seam, we talk about this vessel. I explained it before on the board, but I'm going to explain it again, that this is your separator, and normally you have this end and this end as well. Sorry, let's again just draw another one. Okay, so okay. So this is what we call the seam to seam. So this is the actual L, or what we call seam to seam. And we said that normally seam to seam normally refers to the seam line, or what we call the welding line of the separator or vessel. This is what we call the seam to seam length. So this is the actual length of the separation section only, not the actual length of the separator itself. Okay, now we talked about classical or conventional separator without a mist, and now we're going to talk about the two configurations for the separator without mist, the vertical and the horizontal. We'll talk about the design criteria for both in brief. But first of all, let's go again and refresh our mind about the range of diameter for the droplet that we are looking at. In this case, when we talk about separator without a mist, we said that we will talk about anything above 150 up to 3000 micrometer. This means that you will not need to use the mist because you have a droplet diameter greater than 150 up to 2000 or 3000 micrometer, and which means that I simply can use which means that this statement is also true because I can simply use the calculation method that I used before for the gravity settling at the beginning of the chapter. Those equation or those formulas are still correct, but for this specific type of separators, I'm going to use a new formulas or a new design criteria to make sure that our standard or our design is correct. So simply the design equation will stay the same as before. So now I'm talking about vertical, for example. Now I'm going to talk about vertical knockout drum, which is a vertical separator without a mist. So it's very similar to the vertical separator with the mist. The same equation can be applied, but in order for the design criteria to make sure that it's correct, it has to be as the following. So the diameter, first of all, has to apply that this equation has to always stand true, and you have to make sure, or to make sure that you still understand or remember what do you mean by Q max, which is the Q value after taking the margin into consideration. The second one is the height of the separator has to be, or the total height of the separator has to be equal to small h plus dn plus x plus y, where dn is the inlet nozzle diameter in meter, x is 0.3 of the diameter or the internal diameter of the vessel, and y is 0.9 of the diameter of the vessel with the minimum of 0.9 meter or with a minimum of 0.3 meter for the x value. Okay, and h is the sorry, my apologies. And h is the height of the separation that we calculated from the equation or design equation before. Now the third major component of the conventional separator without mist is the what we call the nozzle, where the nozzle has mainly three types. You have the feed nozzle, and you have the gas outlet nozzle, and you have the liquid outlet nozzle. Normally we refer to the diameter of the nozzle as dn, and for example the feed nozzle, it can be taken as the equal to the feed pipe nozzle as well, or the feed pipe diameter. So if you have a tower, for example here, separator, okay, so the feed nozzle or the size of the nozzle in the feed, which is this one, you can take it as the size of the feed pipe, similar to the size of the feed pipe that's feeding the separator. Or you can follow this criteria where the density multiplied by the velocity square inside this nozzle shall not exceed 1500 kilogram per meter second square. Normally for the gas outlet nozzle as well, it could be also taken as the what we call, and here I'm going to just draw it in different color. Here is what we call the gas outlet nozzle. It could also be taken as the value of the pipe that's leaving the separator, or it can also be followed this criteria as well. And for the last one, which is the liquid nozzle, which is normally at the bottom section, could be here, for example. This is the liquid one. It could also be chosen in a way that to give you a flow rate of or velocity of 1 meter per second, for example, or lower than this one. Now we'll continue with what we call the conventional separator without mist. Here we're talking about classical separator, vertical and horizontal separator that doesn't have mesh or what we call the mist extractor or the demister. Now when we are talking about horizontal knockout drum or the horizontal separator, and so when we talk knockout drum, this means that it's a separator without a demister or without mist extractor. So when we talk about the cross-sectional area, cross-section also can be calculated based on this, where the cross-sectional area is taken above the liquid level, and the Q max is similar to what we have explained earlier, where it includes the Q plus the margin for that specific separator. Okay. And normally the horizontal vessels will be designed in a way to be between 1/3 to 1/2 full. So it's not like always full in terms of when we talk about horizontal separator. So let me just draw the sketch here. So when we talk about this horizontal separator, we design it in a way to make sure that the maximum it can be half full, and the recommended one normally will be between half and 1/3 of the separator. Okay. And also in terms of nozzles, for example, for the horizontal separator, also you can look at these criteria for the feed nozzle, for the gas outlet nozzle, and for the liquid nozzle. And as I mentioned several times, none of these formulas must be memorized. These are the formula that will be given to you in case you need, or you can just prepare it in your sheet during the exam. So you don't have to memorize any of these formula. These are recommended guideline. Okay, so it's more like it's about the knowledge that you know that there is a guideline for this separator, vertical or horizontal, so you don't need to memorize it. You need just to know it and to know how to use it as well. Now let's move to mist extractor and try to understand how the mist extractor work
or due or how it functions in order to remove the tiny liquid water droplet. So we understand already that if you have a larger liquid droplet greater than 150 micrometer, by gravity settling, it's fine. And if you have less, you need to do, or you need to install what we call the mesh extractor. But how the mesh extractor work? And as we explained earlier, the mesh extractor work based on what we call the momentum change. So here you have to, let me just grab the pen. So this is the scheme. It shows you how the gas and the liquid are moving up. This is direction flow for the gas and liquid moving up, and this is the mesh. And in the mesh, what will happen, that you have the gas stream that's moving up, and the gas stream will, what will happen to the gas stream? Will continue moving because it's very light, the density is very light, so it will continue moving. And what will happen to the water droplet? The water droplet will move up slowly with the gas stream, but when it hits, when it hits the surface of the mesh, so the water droplet will move up, and when it hit the mesh, it will stick to that mesh and it will start to accumulate on that mesh, and after certain period of time, several water droplets will also accumulate on the surface. Sorry. This one. This one. Okay. So here is the water droplet, so they will all accumulate in the surface of the mesh, and as a result, the size of the water droplet will start to become large, and then it will fall from the mesh. So this is the basic principle or the basic mechanism how the mist extractor is working. It's a mesh, and this mesh will act as a resistance to the flow of the two fluid, which is the liquid and gas. The gas will continue to move quickly, and the liquid will move slowly, and it will start to accumulate on the surface of the mesh, collecting several tiny water droplets together, make them large, and then they will drop from the mesh. But is mist extractor always used? Not always. In case if you have in the plants where you have the risk of fouling or the hydrate formation, most of the time you will avoid using the mesh or the mist extractor. It's not practical. You will use instead what we call the centrifugal type separators. The design equation to design vertical separator with mist is very simple. You can simply find what we call the critical or the terminal velocity to be equal to K, which is a new constant, and this constant factor is what we call K factor for sizing the wire mesh, multiplied by square root of the difference in the density between the liquid and the gas divided by the different or the density of the gas. This approach is very simple. As you can see, the equation is very simple, but the main issue with this approach is that you cannot always predict how much exactly is the size of the water droplet. And the K value will be obtained from a table that we will see in the next slide. Okay, now let's learn how to get the K value for sizing wire mesh demister in case of the separator with demister. So, and this table will represent value for K factor in terms of meter per second. And as you can see from this value, that it depends on the type of the separator and the configuration of the mesh. If you have horizontal with vertical pad, or if you have vertical or horizontal separator with horizontal pad. Now and there is also, we have to keep in mind that in the node there are certain corrections, but the most important one is the first point, which is the correction for the pressure, because we have to assume, or we have to find how much exactly we are operating the separator. So let's assume that I'm looking at what we call vertical or horizontal separator, and I have a horizontal pad. This means that I'm going to look at value of K approximately equal to 0.107. So if my operating pressure is 1 atmospheric pressure or close to 700 kilopascal, this means that there will be no need for correction. So I can assume that I have the exact same value. So I have 0.107 for the K value. But let's assume that I am operating at 1400 kilopascal. This means that I am 700 above the baseline, where the baseline has at 700 kilopascal, you use the correction value of 0.107. So I am 700 above the baseline, 700 kilopascal above the baseline. And as per the guideline here in point 1, it says that for each 700 above the baseline, you have to subtract 0.003 from the actual value. So if I'm using vertical or horizontal separator, and the pad is in the horizontal configuration, and my actual value is 0.107 for K, and I'm operating at 1400 kilopascal, the actual value or the right value for K has to be 0.107 minus 0.003, because I'm operating at 1400 kilopascal. So the actual value will be completely different than the 0.107. Now let's assume that I'm operating at 2100 kilopascal, this value, which means that we are 1400 above the 700 kilopascal baseline. This means that the actual value for the K in the demister has to be 0.107 minus 2 multiplied by 0.003, because the 1400 which is above is actually 700. So 2 multiplied by 0.003, I subtract this value from the 0.107 to get the exact value of the demister. And the next slide, you will see that we're going to use the same K value, but in terms of foot per second, different unit, and you will get different K factor or correction, and you will see the correction in terms of percentage. And here also in this slide also you can use the correction in terms of percentage based on the pressure that you are using. Also you can get K factor in terms of foot per second, with the correction factor in terms of pressure as a function of pressure. If you have atmospheric pressure, you use the 100% of the value. If you have, for example, 300 psi, then you use the approximately 85% of the value obtained for any type of these mist. Similar to what we did for the vertical separator without demister, we're going to do the design criteria as well for the vertical separator with demister or with mist. The diameter also has to always maintain that this statement is true, which is this equation has to be always true in terms of once we calculate the diameter. The height also, assume that this equation has to be always true. Keep in mind that what do you mean by H capital, H small, and this is all in you can find it here. And this section, what do you mean by H capital, H small, and most of these parameters or most of these definitions we have already explained it in the previous slides. The diameter also has to maintain that this statement is always true or correct, and this is how you calculate rho of the M or rho mixture and velocity of the mixture. Now for the horizontal separator with mist, or what we call horizontal demister separators, we can still use the same equation that we use for the vertical one, but you have to keep in mind that we need to do adjustment, a small adjustment for the length of the separator. Why? Why is that? Because here the separation is taking place in line with the horizontal dimension, and this is the correction for the length that you see. And normally separator length can be any size, but you have always to keep in mind that the ratio between the seam to seam length, or the length that you calculate for the separation, to the diameter of the vessel has always to be in the range between 2 to 1 or 4 to 1, and you can simply use this equation where K value again is the Demister constant. And normally horizontal vessels are normally in the range of 10 feet and up in terms of length. Okay. Okay, let me just clear this one because it's okay. Okay, so that's it. Which is the length. Sorry, excuse my ugly drawing. It's not perfect, but I'm trying to make it perfect. Okay, so here again we said that the length that you are calculating here, or this length, or the what we call the LV, is the length for the separation, which is what we call the seam to seam length, or tangent to tangent length. And Vc or Vt is the critical gas velocity. K is the factor for the mesh or the Demister, as we learned before. And now the last thing is to look at how is the configuration, or where's the exact location of the Demister or the mesh inside the separator. Normally we are looking at something called or minimum extractor. Let me just grab the pen. We are looking for something called minimum extractor clearance, which is this distance, which is the distance from the top of the Demister to the outlet of the gas. And you can see here that we have completely two different configurations. This configuration has the gas outlet at the top of the vessel. This configuration is slightly different, where the vapor out will start to come from point completely different, where you will the flow here, the flow of the gas will be like this, and in this term, no, the flow of the gas will be like this. Okay, this is the difference between the two configurations. But the bottom line that the minimum extractor clearance, which is Cm, can be found as the following: Cm equal to 0.077 multiplied by MOD minus NOD divided by 2, where MOD is the mist extractor outside the Demister, or MOD and NOD is the nozzle outside diameter. This is the difference between the two new definition, which is MOD and NOD.